This is Algebra 2B, probability lesson 3, dependent events. So to contrast the previous lesson, dependent events do affect each other. Did I get that wrong on the last one? Who knows? Okay, do affect each other. This would be, the easiest example would be without replacement. So if we think about our deck of cards, right? There's 52 cards in the deck. So the chance of getting a king of hearts, there's one king of hearts out of the 52 cards in the deck, right? Now, if I'm saying what's the chance of getting a king, 4 out of 52, but then I take that king away, okay? What's the chance of getting a king now? There's only 3 out of 51. So if we don't replace what happened the first time, the second time gets impacted. It changes, okay? The multiplication rule for dependent events looks kind of the same as the one for independent events. The probability that A and B happen. Now, I've seen this A and B, but I've also seen this A then B, so I'm going to go A then B. Really means the same thing as A and B. The probability of A and B, or A then B, is going to be the probability of A, and it's still times, but now it's the probability of B given that A happened. So it looks the same. We're still going to be multiplying. We need the probability of the first event times the probability of the second event, but that probability is dependent on the first, so it's a little more complicated. Let us try a couple. Fill in the missing probabilities. Okay, so starting off at this first event here, right? We see this 80% chance that that event happens. Remember, that also gives us a 20% chance that it does not happen, right? 0.8, 0.2, that's our one whole or our 100%. So if I want the chance that this happens, that's 0.8 times 0.75 to get to A there. 0.8 times 0.75 means that this is a 0.6 or 60% chance that the first thing happens and the second thing happens. Now, to get to B on my diagram, we're looking at this event and its complement. So if there is a 0.75 chance of that happening, there is a 0.25% chance of it not happening. 0.25 chance of it not happening, because that's our 100% or our one whole. So if I want to get to letter C here, that will be 0.8 times 0.25. A, B, C, D. Okay, so I can't use my complements because I don't have D or E. I know that they need to add up to one whole, but I don't know what that would be. But I do see this 0.18 at the back here. So I know 0.2 times something has to bring me to 0.18, right? The probability of A not happening and the probability of B happening would be not A times B. So I'm going to work backwards. I'm going to divide. If I do 0.18 divided by 0.2, it will tell me that this guy right here is a 0.9. Now that I know D, I can find its complement at E. Those got to add up to one whole. If I got 0.9, I need 0.1 to get up to one whole. And then finally for F, this is A not happening and B not happening. I can multiply those two paths together. 0.2 times 0.1 is a 0.02. Now, if you wanted to check your work, remember all of these should add up to one whole because they represent 100% of the possible outcomes. So that is 0.6 plus 0.2, which is 0.8. And I know 18 and 2 is another 0.2. 8 and 2 is one whole. So for sure, they all add up to 1. Letter B. A jar contains 4 red marbles and 3 green marbles. A marble is drawn, not replaced, and then a second marble is drawn. Let's find each probability. Okay, so we have 4 reds and 3 greens. So the probability of drawing a red would be 4 out of the total. 4 plus 3 is 7. So I have a 4 out of 7 chance of getting a red. Now the complement to red is green, so I just got that labeled with a G for green. There is a 3 out of 7 chance of drawing a green. Okay, now if we add that up, 4 sevenths, 3 sevenths, that's 7 sevenths, one whole. Now, whether we got a red or a green, we did not replace it. We didn't put it back. So I'm going to the top. I had a 4 out of 7 chance of pulling a red. I got rid of that red because I pulled it out, didn't place it back. So now there are only 3 reds left. That's why this second probability, red given red, is dependent on what we pulled. So now there is a 3 out of 6 chance of getting a red. I lost a red, so there's only 3. That also takes one from the total, so there's only 6 in the total. Chance of getting a green is 3 out of 6. So the probability of red given red is 3 out of 6. The probability of green given red is also 3 out of 6. Let's look at that bottom trail, okay? Now, on that bottom trail, I did not pull a red, I pulled a green. So if I pulled the green out, didn't put it back, now there's only 2 greens left. So the probability of red, given that I took out a green, there are now 4 reds left out of the 6 marbles. The probability of green given green, there are 2 greens left out of the 6 marbles in the jar. To get the probability of red and red, we're going to do the probability of red. How do I want to write this? Let's write this. To get the probability of red, we need the probability of red times the probability of red given red. Okay? So that's 4 sevenths times 3 sixths. Sixths is hard to say. That would be 12 out of 42. 3 times 4 on the numerator, 6 times 7 on the denominator. Okay? And we want to reduce that. I'm not sure if I want to or not. Maybe I will. I'll put it way at the back because I didn't leave myself enough space. So if I wanted to reduce that, that's 2 sevenths. And if I wanted to go a little bit farther, I can get that's approximately 29%. 29%. Okay. Probability of red-green. We need the probability of getting a red times the probability of getting a green, given that we took out a red. So, following the path, that's 4 sevenths times 3 sixths. Hey, that's the same exact answer. So again, 2 sevenths is about 29%. Yikes. Third answer, probability of green and then red. We need the probability of a green times the probability of a red, given that a green was removed. Okay? We're going to multiply along the paths again. 3 sevenths times 4 sixths. Is every one of these the same answer? In the numerator, 3 times 4 is 12. In the denominator, 7 times 6 is 42. That's another 2 out of 7 chance, still known as approximately 29%. And number last. We'll get a new answer on this one. Probability of green and then green, double green. It's the probability of a green times, the probability that we get a green given that we pulled a green. Okay. Probability of green is green times green given green. Lots of G's. Numerator times numerator. 3 times 2 is 6. Same denominator. And if we reduce that guy, that is a 1 out of 7 chance, which is approximately half of that percentage. I almost wrote the same one. 0.14 or 14%. Now, if you look at our outcomes here, we have 2 and 2 and 2 makes 6, and 1 more makes 7. 7 out of 7 is 100% of our possibilities. And he done. Last one. Find the probability of each event when drawing from a standard 52 card deck without replacement. If you need it, on the very, very last page of this packet, there is a list of all the cards in a standard deck of playing cards. If you have a lot of history playing cards, you might already know that there are 4 suits: hearts, diamonds, clubs, and spades. There are 13 cards within each suit, starting from 2 all the way up to 9, 10 for numbers, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then they go J, Q, K, A, Jack, Queen, King, Ace, making 13 altogether. Generally, we call the face cards, ones with faces on them, Jacks and Queens and Kings. So, with all that, what's the probability of getting 2 blacks? I think I want to look at the handout. There he is. Okay, so probability of getting 2 blacks, I think was what the first one said. Right now, there are 26 black cards out of the 52 cards altogether. So you can say 26 out of 52. You could also just say 1/2 because exactly half of the cards are black. But then if we take away a black, doesn't matter which one we take away, okay? Then it leaves us with only 25 out of 51. Because if you take one away, it's no longer 26, it's 25. We take one away, it's no longer 52, it's 51. So back to the packet page. There's going to be a lot of annoying scrolling, isn't it? We got to be getting close. There he is, 2 blacks. That will be 1/2 times 51. That's my denominator. 25. Now, you could have done 26 out of 52, but that's going to be a little more work when we go to multiply. So that's why I reduced my first fraction. That gives me 25 out of 102. Now, if we want to get that as a percent or decimal, that's about 25%. I'm going to keep the decimal, 0.245. So it's a 24.5% chance. What is the probability of drawing 3 hearts? Okay, now we're drawing 3 cards. I'm going to just do this without looking at the paper, but if you need to, you can. What's the probability of drawing a heart? Right now, I know that there is 1 out of 4. You could also say 13 out of 52, but I know that it's 1 out of 4 because we have 1 suit of hearts out of the 4 suits. Now, if you take a heart away for our second fraction, okay, now there's only 12 left out of 51, and I'm keeping those numbers big because you really can't reduce that fraction. Now again, take a heart away. Now there's only 11 out of 50. Okay? So it was 13 out of 52. then 12 out of 51, then 11 out of 50. Every time we take a hard away, we have to give the second fraction given that happened. So if we were going to multiply these all out, let me get rid of this guy. In the numerator, that is 132. In the denominator, I don't know what that is, 4 times 51 times 50, big number. 132 out of 10,200. If we wanted to get that as a decimal percent, that is approximately 0.013. We'll round it there. So it's about a 1.3% chance. Last one, probability of 4 aces. We have 4 events. We're going to need to do 4 fractions and multiply them all together. I'm going to keep these unreduced too, okay? Just for fun. So in the numerator, what is the chance of pulling an ace? Right now, there are 4 aces out of the 52 cards. You could also say 1 out of 13 if you wanted to reduce it, but I'm going to keep this one unreduced just so we can see what's happening really clearly. Now, if you take an ace away, don't put it back. Now there's only 3 aces left out of the 51 cards left. Again, you take an ace away, you don't put it back. Now there's only 2 aces left out of the 50 remaining cards. And one more time, if we take an ace away, there's only 1 ace left out of the 49 remaining cards. Multiply these, we go straight across. 4, 3, 2, 1 on the numerator gives us 24. And in the denominator, he gonna be something crazy. Okay, 52, 51, 50, and 49. 6,470,400. One more time. 6,497,400. So the chance of drawing 4 aces from a deck, one after another, would be 0.0012, 2, 3, 4, 5, 3, 7. Let's go that. That's the chance of that happening. Even if you made it a percent, it's a very, very, very tiny number. That's all I have for you today. Good luck on the exercises, and please let me know if you have questions.